master's and PhD, both from Aachen University under Hermann in Germany. So thank you.
Thank you very much. So, first of all, I would like to thank Bill Byrne for inviting me to this seminar series and giving me the opportunity to present my work. So, the title of my work is Dynamic Programming-Based Search and Segmentation Algorithm for Statistical Machine Translation. So, the dynamic programming-based part is based on my PhD thesis, and the segmentation part is based on recent work at IBM. So, this is the overview of my talk. So I will present dynamic programming-based techniques for statistical machine translation. And the first two-thirds of my talk I will present dynamic programming-based decoding algorithm for the IBM Model 4, and I will shortly explain what the IBM Model 4 is. I will show how this problem is related to the traveling salesman problem. And in this third, like in the second part of my talk, I will present dynamic programming-based segmentation algorithm for a block-based translation model. I will motivate what I mean by this, and I will sketch that this is related to the set cover problem. So these two problems are in general NP-hard problems. So I will come up with certain restrictions on the problems that I consider, such that the optimization problems I consider become sequential decision problems under appropriate restrictions. I will show what these restrictions are. So this is the overview of the search part of my talk. So I will present the dynamic programming solution to the traveling salesman problem. I will show how the traveling salesman problem is related to the word ordering problem in statistical machine translation. I will show how the dynamic programming solution to the traveling salesman problem can be applied to statistical machine translation. And I will introduce two kinds of restrictions under which an efficient dynamic programming search algorithm exists. One restriction is taken from the IBM Candide system description in the pattern description of the IBM Candide system. And I can show that for the full search, making the model assumptions I will present on the following slides, I get an upper bound for the search complexity of e to the 2 times j to the 4, where e is the size of the target language vocabulary and j is the length of the input sentence. So for the translation direction German into English, there's a need for a different reordering restriction that is associated with the German verb group, and I will show this restriction as well, and I will give an upper bound for this restriction as well. So then we'll present a data-driven search organization in connection with the dynamic programming-based search algorithm. So this is the overview of the IBM Candide machine translation system. So given is a source language source language sentence that is translated into a target language sentence. So I'm using the notation F for the source word, having in mind the translation direction for the old Candide system was French to English. So I'm translating in English a source sentence of length 1 to j, with, consisting of j words, into a sentence of length I, ei to I, and I might apply some transformation steps to the source and target language in order to make the translation process in order to make the modeling for the translation model simpler, and in order to make the search process simpler. So given the source string, I translate into the target. I'm looking for the most probable target string, and that's equivalent to maximizing this product where the first factor is the language model probability. I use the triangle language model for the language model probability. And the second factor is the translation probability. This is called the source channel model. So this is the overview of the IBM work, the original IBM work introduced this alignment concept. each source position is mapped to exactly one target position. So this is an alignment example for the translation direction German to English. So this is taken from the Workmobil domain, which is an appointment scheduling domain. German sentence is, in diesem Fall kann mein Kollege Sie am 4. Mai nicht besuchen. So at my old place at RWTH, we had this two-dimensional way of showing alignments. So then we show the target word that is associated with each source word, and this result is a kind of alignment path, like in speech recognition, where the states correspond roughly to the target positions. And then drawing connections between these alignment points, you can already see that this is not monotonic, so there's a word order difference between German and English, and we have to cope for the word order difference. So then using this alignment concept, the translation probability was modeled as a sum over all these hidden alignments. So these are some details, some model details. So I used the trigon language model for my translation experiments, and a translation model. I introduced some simplified notation. So there are basically three kinds of probability distribution in the IBM model for lexicon probabilities between single source and target words. Fertility probabilities. The standard example is like the English negation goes to two French words ne pas. So generally not translated as two French words, and they are class-based distortion probabilities. So I don't show the class here for simplification purposes. So this is a probability on the order in which the source positions are processed. So this would be able, using this one is able to model things like that adjective follows the noun in French. So for my experiments, I've been using, I have used the IBM 4 implementation that has been done here at Johns Hopkins University in '99. And in particular, I've been using an extension of this, which is called Visa++, which is now which is used at other places too, and which is due to Franz Josef Och, and which builds upon Visa. So this is some overview of a related decoder work. So there's no paper about the IBM Candide system decoder. There's a description in the patent, in the IBM patent, which is 96. So my decoder is somewhat related to this. I will explain details on the following slides. So there's work by Dekai Wu. So he uses the IBM translation model, and then he introduces a decoder which has bracketing restrictions on the reordering. So I won't go into the details. So I just mentioned that assuming that each source word is translated as exactly one target word, he has a complexity of J7 for his search algorithm. So then there's some work on so-called monotonic genomic programming search, which I did back in '97. So this assumes a monotonic word order between source and target language, and then one can come up with a very efficient dynamic programming decoder. And this assumes that the source sentence is preprocessed using some rule-based grammars that reorder the source string so that it can be translated monotonically. So there's work by Sonja Niesen, also RWTH, introducing the so-called inverted alignments. I will explain this on the next slide. And there's work by Kevin Knight's group, published at ACL. So Kevin Knight, this paper contains 3 decoders for the IBM Model 4. So one is the implementation of the stack decoder in the Candide system. One is the greedy decoder, starting with some gloss as translation, then trying to improve this by carrying out swaps and replacements of words in on the string and greedily improving the translation. Third one is just mapping the translation problem to a traveling salesman problem and using some standard package for solving traveling salesman problem. But this works only for very short sentences. So there's a A-star implementation. So these things belong together somehow. So plain A-star implementation by Franz Josef Och. So he looks at some criteria to carry out, like to guarantee that he finds the optimum. And this decoder as some extension of the decoder I am presenting here, producing word graphs, translation word graphs. So now I'll explain this word alignment concept. So for the regular alignment, you would map source positions to target positions. So the problem of that would be if I possess some source position, I generate some target word. So I put the target word at some position in the target sentence, and I might not know the predecessor target word. So I don't know the language model cost for this word at this point. So I reformulate this alignment concept. So I now map target positions to source positions. In our two-dimensional way of showing alignments, we could produce the output sentence from bottom to top, and we are sure that for each hypothesis that we try in dynamic programming search, we know all its predecessor hypotheses. So then we have to add an additional constraint, which is not in the alignment notion. We have to add the constraint that each source position is processed in this. So we have to account for all source positions in the input sentence.
Do you mean processed, or it has to be assigned to some target word?
Processed. It might be assigned to the empty word. Right. It has.
But you may reject it.
No, you don't. You do have to do something. You have to do something with it. You can't produce.
Okay, so it has to be assigned. I mean.
Yeah.
It has to be the father.
It has to be. It has to produce something. It has to
produce something.
Right. So it has to. So I look at the position, I produce something, and then I mark it as being. I'm not looking again at this position.
Right.
So I might be producing. There are several possibilities. So I'm simplifying here. For the IBM4 model, you could either assign it to the empty word, or you could assign it to the same target word if the fertility of the target word is greater than 1, or you could produce a new target word. So, but it means I'm looking at this position and I'm.
You keep pointing it somewhere and then it goes somewhere else. So what are you talking about?
Okay, let me go back. Let me go to the next slide.
Okay.
So I will show what is covered.
What I don't understand is whether those points, those empty circles, which are connected by that line.
So this is just, this picture is not very detailed. It just shows that I want to carry out some kind of dynamic programming optimization where I build the translation hypothesis from bottom to top, and I know, so I have to have a way of showing that the predecessor hypotheses are like, that I have full knowledge, that these partial hypotheses that I build up have to, if I go to the next one, that I have the full knowledge of everything I need to extend this hypothesis. So let me go to the next slide. That's what I explain it. So now I explain the traveling salesman problem. So we have J cities, we have costs for transitions between cities. So we have to visit each city exactly once, minimizing the overall cost. And then there's a dynamic programming solution for that problem, which is due to Health and Carp in 62. You can find this algorithm in some optimization textbooks. And then the cities roughly correspond to source sentence positions. And the thing that is important is that each source sentence position has to be so in the generation process, each source sentence position has to produce something only once. So it has to produce some word exactly once. So like each city has to be visited exactly once. So now we'll sketch this dynamic programming solution to the traveling salesman problem. So I'm evaluating the following, the dynamic programming solution to the traveling salesman problem evaluates the following auxiliary quantity. So this C is like, it's like a set representation of the cities that I've already visited. So I'm talking about coverage vectors, meaning the set is represented as a sequence of zeros and 1, where 0 means the city has not been visited yet, and 1 means the city has been visited. So I'm assuming this coverage kind of representation of a set. And then the meaning of this quantity is it's the shortest path from city 1 to city j, visiting all cities in C. So now we'll skip to the next slide. So what this means is, so the brute force method of generating all the permutations would be trying all, of getting the optimal tour with generating all permutations. So, but I can do better by generating these tuples in the dynamic programming approach, and for a given set of cities and ending city, it's not important in which order cities have been visited. So actually this cannot be, okay, I will point it. So this tuple means, so this is, this diagram shows traveling sales from the application of the algorithm to a traveling sales problem of 5 cities. So this tuple means I've visited the city 2, 1, 3, cities 2, 1, 3, and 4. The last city visited is 4. So, and I might have visited either first city 2, then city 3, or city 3, or then city 2. And at that point, I don't have to consider these two options. I can store the minimal value for the best of these two options. And if there's problem involves more cities, then the network, the lattice gets more complicated. So again, these cities would stand for source sentence positions. So this might be a translation graph that my algorithm searches for input sentence length 5, provided that each source word produces exactly one target word. So this equation is evaluated recursively. So the brute force approach would be generating all possible permutations, and this can be reduced to complexity j to the 2 times 2 to the j, where j is the length of the number of the cities, and you can read off this complexity of this recursive definition. So these are the coverage sets. So there are 2 to the j possible subsets, and you get 1j for each ending city, for each final city in the tour, and then you get 1j optimizing over the predecessor cities. So, okay. Oh, okay. Now, how is this carried over to machine translation? So the original problem was finding the target sequence given the source, the target sentence given the source sentence that maximizes this product. So we're searching the maximum approximation, meaning we are not carrying out the sum in this translation probability. So then we are searching over these inverted alignments. So then I can take Held and Karp's formula, and I can extend it like follows, assuming the use of a bigram language model. So we, in our partial hypotheses, we have to keep track of the final target language word. So then we have lexicon probabilities and distortion probabilities. Otherwise, the formula would looks very much the same, and we get a complexity of e to the 2, which comes from the language model, from the size of target vocabulary. Okay, times 2 to the j times j to the 2. So now this cannot be, we cannot carry out a computation for even medium-sized sentence. We have to further restrict the coverage vectors that occur. Yeah.
Yeah, just to check that we're following you so far.
Yeah.
Kevin Knight wrote a paper on doing translation with finite state devices,
Right.
in which to handle this problem of arbitrary reordering to introduce a permutation lattice. Now this is essentially the same solution, is that correct?
No. Actually, he wrote a paper. That particular paper I don't know. But he wrote also a paper in computational linguistics showing that the IBM1 decoding problem is using a bigram language models generally and p-hard. So I'm
yes. Well,
I'm showing it's under certain restrictions I can handle this problem. So I don't know this paper about this finite state thing.
Yeah, he introduces a finite state machine which looks exactly like the lattice that you described a couple of slides ago. That's where a state keeps track of what's been generated.
But this lattice grows really huge if you.
Of course, yes, it can be exponential size.
Right.
And your algorithm so far takes exponential time.
Yes, so far it takes exponential time. So that's how this recursive equation is evaluated. So I have an input string of length j. So I'm evaluating this equation. So so I evaluate this in a way that what I call cardinality synchronous evaluation. What this means is I generate these hypotheses. I generate the hypotheses in the search process one column at a time, so that all active hypotheses would cover subsets of a given cardinality. So these subsets have size 1, then I generate all subsets of size 2, all subsets of size 3, and I will use this for my pruning that I will show. So this is one restriction under which an efficient search algorithm. The restriction now? I will show
you.
You
just say this is one restriction. What is one restriction?
I will present two restrictions under which the search problem can be carried out efficiently.
You haven't presented it yet.
No, this is the first restriction. This is the first restriction under which the generic coding search algorithm I just presented can be carried out efficiently. It is taken from the IBM style. It is taken from the IBM Candide patent description. So the patent contains a procedural restriction. It has these coverage vectors. So I show positions in the source sentence that have already been processed as filled dots. I show positions that have not been processed yet as unfilled dots, and I show positions that may be selected next for processing as shaded dots. So what this restriction says, it says given a coverage vector, I have to choose one of the four already not already covered source positions. So this means I process the sentence mostly monotonically. I can leave holes in the processing. So the number of holes I can leave in the monotonic traversal of the input sentence is restricted. So this translates into the fact that the number of holes in the coverage vectors that I'm considering my search is at most 3, is smaller or equal 3. And then I can show an upper bound for the complexity of e to the 2 times j to the 4. So another restriction is motivated for the translation direction German into English. So here we have the problem of the German the word order difference is mainly due to the German verb group. So the German verb group decomposes into a left and a right verbal brace.
Left and what?
Left and right verbal brace. So for example, so the German sentence is: In diesem Fall kann mein Kollege Sie am 4. Mai nicht besuchen. So the verb group, which is the core of the verb phrase, would be kann, and the modal verb kann, which is can, and the infinitive besuchen, which is visit. And in English, and then the negation particle in German goes with the infinitive. And then in English, the verb group is occurs at contiguous positions. So what I have so far, I still assume a monotonic traversal of the input sentence. So now I can leave holes in the monotonic traversal, and I can move words in the monotonic traversal, like moving words from further behind in the input sentence, which is something like leaving holes in the set of not yet processed positions. And I have. So in German, I skip the position of the finite verb and then first translate the noun phrase that is the subject, and then translate the finite verb. And then I can move words from further behind in the sentence. And I have number restrictions on the number of loops I can leave, and the number restrictions on the number of words that I can move. And I have window restrictions on how far I can skip. How far I can move words and how far I can leave holes in the monotonic traversal. And then this is coded in this upper bound. So R is the number. R is the distance that a word may be moved, and L is the distance that a verb may be skipped. And I can move 2 words, resulting in a complexity of R squared, and I can skip one. I can skip one position without being in a complex. Okay, the details are my PhD details, so I get an upper bound for this kind of URL restriction. So how is this connected to? So now I'll present beam search approach to evaluate this dynamic probing. And doing beam search approach in connection with this dynamic probing algorithm, the search proceeds cardinality synchronously over coverage vector C. I will show this. I mentioned this already. I will show this on the next slide. There are three types of pruning, which I call coverage pruning, cardinality pruning, and observation pruning. So the coverage pruning would be applied to all subsets of source positions that would cover this, that would cover the same subset of source positions. Like, for example, this subset is these two hypotheses would be pruned jointly under the coverage pruning. So actually these are marked as red, are not quite visible. So and then these. So whenever I have a tuple that covers the same set of input positions, I can prune this under the coverage pruning, and then the cardinality pruning would prune partial hypotheses for which the input set would have the same cardinality, meaning all the partial hypotheses in one column would be pruned jointly. And I have four kinds of parameters associated with this pruning. So I compute the best score for each coverage vector and each cardinality, and I keep only those hypotheses that are within a beam of this best score for both coverage vector, for all coverage vectors and all cardinalities. I also use histogram pruning, saying for each coverage vector I keep only the best 50 or so partial hypotheses. So these two kinds of pruning are identical in speech recognition, where there's no vertical alignment problem. And then this third kind of pruning is observation pruning. For each source word f, I select only restricted number of the best target words e, according to this product of translation probability and union probability of the target word. So I will keep only the best 12 or so. I will generate only the best 12 or so partial hypotheses for each target, for each source word f. So these are some translation results for the translation direction German to English using the IBM Model 4. So the evaluation method, these experiments were carried out 2 years ago, so we didn't have blue yet at that point. So evaluation method measures were multiple word error weight. So instead of having one reference translation, we had several reference translations and computing the word error weight against all reference translations and taking the minimal word error weight. And then there was a subjective evaluation criterion where a human judge could assign a score from 0 to 10 to each translation. And then this was processed as an error weight. Then, this is for the German workmobile task, where the training set is rather small, only 60,000 sentence pairs and a relatively small vocabulary. And we had two test sets, one development test set on which the optimal pruning. So there were some parameters in which the model parameters were set. These were basically like language model scaling factor. And the pruning experiments were carried out on this development corpus as well. And then we had a evaluation corpus on which we evaluated the final translation performance, also computing the subjective sentence error rate. So these are some coverage pruning effects for the two wording restrictions. GE wording restriction is for the translation direction German into English, and S3 stands for skip 3, leaves 3 holes for the IBM style restriction. So the complex upper bound for GE restriction is lower than for the S3 restriction. So generally the search can be carried out faster. So then I report the coverage pruning threshold as its negative logarithm. So you can see as you increase the coverage point threshold, you retain more hypotheses in the beam search, and so on the evaluation data, the more multiple word error rate goes down almost consistently. So this is the CPU time per second. So the S3 restriction is generally, because it's higher theoretical upper bound on the complexity. For the same pooling threshold, it takes several times longer to carry out the decoding, and for example for the pooling threshold 10 point, for the pooling threshold of 10, the search using the S3 restriction cannot be carried out due to memory and time restrictions. So on the evaluation data, the multiple word error rate for the GE restriction is smaller, presumably because the German work group effect is better modeled using GE restriction.
Christoph, can you quickly tell me what this multiple word error rate is?
Oh, so you have, like in this case, we had 331 test sentence.
Yeah.
We had on the average 6 reference translations per test sentence. We compute 6 reference translations per test sentence. And then we compute the minimal word error rate, like computing the word error rate for each sentence and then taking the minimum.
Okay. But you're calculating word error rate in the usual edit.
Right.
You do a Levenstein alignment.
Yeah.
And then you see what the error rate is.
Right. And then
so
I
you
do.
don't care about the sequence. I mean,
So actually,
English could be completely non-English, and
no.
I mean, syntactically, could it be completely wrong as long as the words are there?
Yeah, but if the word order is totally screwed up, then it will not. The word error rate will show this. I mean, I'm not just computing. I'm not just looking whether the word is
from
right.
an English point of view or screwed up.
From English point of view.
Then I don't understand.
So basically, this is word error rate except that
Word error rate, like in speech.
Except there are 6 possible corrections.
6 possible reference translations.
I see. So we don't straighten out anything.
No.
We cannot permute words.
No.
We can only shift them.
So actually, I think Al-Shabi did something like this. So these reference translations were produced by a human translator. I asked him to be as to translate the sentences as possibly as much a word-to-word basis as. And then part of the reference translation were obtained by carrying out the automatic translation and then correcting the automatic translation as well. So these were exact, like as possible as these were word-to-word translations as could be carried out reasonably by a human translator. So these are results on the evaluation test set. Now I compare this to the monotone no reordering restriction, so I don't carry out any reordering. And then the multiple word error rate goes up. And because if I don't know reordering, this shows in the translation performance. And then this GE and S3 restriction, which are the workgroup and the IBM patent restriction, perform at about the same level, where the S3 restriction is about 2 to 3 times lower than the GE restriction. And the subjective evaluation corresponds roughly to the multiple to the word error rate. So if you would compute blue on this test set, you would see probably very similar results. Like blue would correspond to the multiple word error rate. Franz did experiments with this.
So Christoph, the
Yeah.
monotone is like an S0
Right,
assumption.
S0.
Okay.
The decoder has this parameter. Just I can decode S0.
Yeah, and S3, like you explained, means that when you're going through the source sentence left
Right.
and right, you don't want to leave too many holes.
Right. You
What is
cannot leave. You can make at least at most 3 holes.
Right. And what is the GE essentially saying if you encounter a part of a work group, then you are allowed
No, it's just a
look at it.
It's just a combinatorial restriction where you allow to skip positions and you allow to move positions. So this is like leaving holes in the monotonic traversal and moving some restricted number of positions from further behind the sensor. It's formalized in my PhD thesis.
But I suppose that this S3 is congenial to French, right? And
Yeah.
because English and French are the same language,
Right.
essentially.
So
And German is quite different.
Right.
Because of the verb.
Right.
So
S3 is not a
good.
S3 is not appropriate for German because it cannot handle the German verb group. So we have to come up with something else.
Right.
So in the German, do you have any way of controlling the number of modals and passives that are present, since that introduces the,
Right.
I mean, if you have active verbs, you can go straight ahead, without having to
So it's just
invert.
I cannot model, like, for example, if I have a subordinate clause that is like moved into a verb group, I cannot handle it. It's not being handled currently.
Could you put that sentence on again?
You mean this sentence?
Yeah, that's right. So, of course, you could pre-process it, right? And you could
Right.
put the link besuchen next to the com.
Right. We did
And
that
before
actually.
you pardon?
That actually we did that at some earlier stage, and then we processed them.
And how does that work?
So first of all, you have to put a lot of hand pre-processing to this because you have to write a path that recognizes the subject, noun phrase.
I see, and there are no good German parsers.
I haven't looked into this, but I wanted to have.
We now have pretty good English parsers, so are there, I mean,
So
there's a guy named
So-
Reitzler, what was his name? Is it Reitzler or Reitzler?
Right.
So
You could
I
use
think
this.
he has good parsers.
Yeah, but I've been looking into simple combinatorial restriction. For example, we have been using this for translation direction Italian to English or whatever.
Yeah.
So then this is like a simple parameter where I can play with this parameter and reducing the search space. And then I get these I get these upper bounds which are like give some kind of understanding of the search problem. You could include these parsers and then formulate the reordering restrictions. Similar reordering restrictions. You could either carry out the reordering, then the question is how reliable this can be done, how reliable this can be done. You could come up, include the output of a parser into this combinatorial restriction, then you would come up with some other complexity, upper bound complexities. Upper bounds of the complexity. But this is just, I was trying to formulate some simple restrictions under which an efficient algorithm exists. So which then gives some understanding how difficult the problem is, because generally it's NP hard.
I had a question about the estimate. If you could go forward to the slide where you have the 3 comparative results. Yeah, right here. So in here when you do the monotone, you don't do any pre-processing, right? Or do you?
No, there's no pre-processing. There's no rule-based pre-processing.
So if you did some pre-processing, do you think you would get very close to the S3 or the GB with just, let's say, a couple of hundred rules or something?
With a couple of,
Something.
Something like that. You would get something like that.
Okay. So
Probably, right. So I will briefly sketch what I'm currently working on. So this is now not decoding, but modeling. So this example is taken from the Brown 93 paper. So it's a French-English alignment example. Les pauvres sont diminués. It's translated into English. The poor don't have any money. And if you this paper used the notation if the phrases cannot be translated on a word-to-word level, they join the English word into one clump and then map it jointly to the source clump is mapped to an English clump. So I will use the I will I will use this two-dimensional way of showing this showing these alignments. So for this end-to-end mapping, I use I will use a block representation of the of these end-to-end translation units. So I will show this on the next slide. So I will assume translation units that are blocks. A block is a pair of clumps, and I will look for a segmentation of a training sentence pair using these blocks, and I will try to account for all source and target positions. This way, the reason is that I want to learn the segmentation in a consistent way, such that it covers all source and target positions. And I don't assume an internal structure for the blocks. So I show the blocks as uniformly filled by these dots. So blocks are pairs of clumps. Clumps are contiguous sets of source and target positions. I don't assume, like I always said, I don't assume an internal structure for the blocks. I compute the unigram, so I'm collecting these blocks on training data, and I collect co-occurrence counts of blocks on training data. I compute the unigram probability of a block over the sum of all blocks that I've collected in training data. I compute the probability of segmentation using these blocks as a product of those unigram probabilities. And as this problem is related to the set cover problem.
Excuse me, when you have that P of B equals N of B, etc., these are not particular blocks, these are just, they don't have words in them, is that right? They just have spaces.
They're defined.
What is B? B is specified by what?
B is a pair of clumps, and clumps are sets of source and target positions that are contiguous.
So a different B is a different pair TS, where T is a number and S is a number.
No, T is not a number. T is a set of target positions, and S is a sort of source positions.
So this is just positions, there are no words in them? Or do you actually put the words in?
That was my question.
No. Okay. So if I speak of sets, I speak of positions. But when I speak of unigram probabilities, I keep in mind I'm having in mind the words at those positions. So I compute this unigram probability.
So P of B is the probability of that pattern and being filled by particular words.
The P of B is just the probability of the words, of the sets, of the number.
Of the German and English words, for it.
Of the German and English clump.
So if you define the clump, let's say as...
So I'm collecting the blocks on training data. So I'm collecting a set of blocks, and then these blocks are sets of German and English words.
Could you put out the slide where you have the blocks?
So is this like an entry in a phrase dictionary, for example?
So one block is one of these rectangles. Is this correct?
Right.
Pardon?
Yeah, right.
Right. And now the probability of that block is the probability of, it comes from the frequency of having observed those English words and those German words in correspondence.
Right.
Could I ask for an example?
Yeah.
Could you take a German sentence which begins with am Morgen such and such, and then another sentence which says da da da.
So I have this French-English example.
Something where a phrase can occur in either of several positions. And
so what's the block
Same
here? The
translation.
block is don't have any money together with some
Same translation.
Right, the words, not the position.
Yeah, but surely that appears only once in the entire training data.
That might not be, that's not true. If the training data is huge, it might not occur only once.
It may have don't have any money with some MEV. It may have many times.
It might occur a couple of times.
What
All
about?
right, but that probability then is very,
So I'm describing
very
what I'm
not robust. I mean, it's,
Right.
I don't know.
So I'm just describing what I'm kind. So but the argumentation that I'm using is so I will have these sets that are blocks, and I will discuss under which restrictions the so my translation model parameters are these blocks, and I want to carry out the segmentation using these blocks, and I will discuss under which restrictions I can carry out these. Carry out this segmentation, then my argumentation works for any cost assignment to the blocks. So the union probability is just used in the experiments. So this, supposing I have these blocks, and I cover. So this is a hard problem because I have an exponential number of segmentations using these blocks in target and source language. Plus, I still have the block reordering problem. So I've been thinking, I'm collecting these kind of translation parameters on the training data, and I'm carrying out, I'm trying to carry out the segmentation using these blocks, and so okay, the dynamic programming solution for these block-based translation models does exist if the target and source positions are contiguous. So there's still this block reordering problem, and I will show under which conditions an efficient dynamic programming segmentation algorithm exists using alignment anchor points.
One more clarification.
Right.
Is your definition of block in any sense maximal? So
I will come to this.
Okay, you'll come to that.
So I'm assuming underlying word-to-word alignment, which might be produced like by the Visa program, and then I'm trying to collect blocks that cover these anchor points, and I will show restrictions on the blocks that cover these anchor points under which the efficient dynamic programming segmentation algorithm exists. So I can collect these blocks covering different anchor points, and these blocks are nested. So I will exclude some blocks. For example, this block is excluded. So this argumentation works for arbitrary cost assignment to the blocks. I'm just looking at the segmentation task using blocks segmenting target and source language. So this block is discarded because I have a kind of closure restriction on the blocks where I say that we allow only blocks for which all the anchor points corresponding to source and target clump have to be included in the block. So this anchor point is not included. It's not included in the block. So it's not included in the target clump. So I will discard this block. So similar, this block is discarded because this anchor point is not included in the source clump. So the reason why I'm doing this is, so if I have general segmentation problem, if I have only clumps as segmentation units for the source and target sets, and then there's only a quadratic number of these clumps. So if I were to collect blocks, I might go forward and allow gaps in the blocks. Allowing gaps in the blocks, I would have the number of clumps would I would have general sets as clumps. So the number of clumps I would have an exponential number of clumps, and so I avoid this by introducing this closure property. And another reason why I do this is I might select this block, and I might select another block covering this anchor point, but I want to avoid all blocks. I want to avoid segmentations that cover any source or target position more than twice. So I can show that under this restriction, the segmentation task using blocks can be carried out efficiently, and its complexity of this algorithm is quadratic in the length of source or target sentence. So either source or target sentence. So the theoretical description assumes a bijection between source and target position, then the source and target length are the same, but then I can show leaving out some columns and rows in the alignment that the normal problem solution for the segmentation task still exists. So these are some experimental results. This I've trained this on 850,000 training sentence pairs for Chinese English translation direction, which is a large training condition in the NIST evaluation this June. So I'm currently not carrying out the segmentation, but I'm using this closure restriction I've presented. I will show in the next slide why do this. So I cannot carry out segmentation, so it's not for time reasons, for space reasons that I cannot carry out the computation. So the segmentation is only carried out during decoding. So and then I have a simple, so I collect these blocks of the aligned training data. I apply this closure restriction, and then I collect all blocks that occurred at least twice. So it's a very simple selection criterion, and this way I collect 4.6 million block features, and I obtain, using this unigram probability on the blocks, I obtain a NIST score which is quite close to the best system. So again, so what I'm doing is, so I have this word-to-word alignment. I'm collecting the blocks of this word-to-word alignment under this restriction, closure restriction. This gives me like 20 million block features. Then I prune away all the block features that occurred only once, and then I compute unigram probabilities of these features, where feature is a set of source and target words. So the confusion might come from the fact that as viewing this blocks as units of a segmentation, I'm dealing with target and source positions rather than words. But for computing the unigram probability, I look at the words. So this is how the decoding is done. So we're using a joint model, like a transducer. So the target sense and its segmentation is unknown. We apply blocks to the input sentence. The clumps also, we're optimizing all possible segmentations for which the source clump yield a segmentation of the input source sentence. And then we are applying a translation probability, which is unigram probability on the blocks, and the language model probability, which are exponentially weighted, and not this weight is not trained. So then for the decoding, we don't reorder these blocks in the current system, and this beam search procedure is similar to the beam search procedure for the IBM4 model.
So I guess in some sense that's almost making a claim that most of the reordering is local.
Right. Right. And this closure restriction on the block means that I collect only blocks that include all the local reordering.
Is the language model on the ordering in the blocks, or is that like on the English side?
On the English side, just. It's not on the blocks. Okay. Language model. So then the question is how you model this, and the language model is applied just on the English words, so English clumps. So why is this working pretty good? So it's kind of an explanation attempt. So this is an example taken from the Chinese English training data. The Chinese phrase is Genuine News Agency Beijing date, where date is the date label. And so I'm not showing the Chinese characters here. So I'm collecting all these blocks on the training data, and I'm seeing the small fragments which make up the big example. So these might occur a couple of 100 times, and this thing might occur like 3 times or so in the training data. So the observation is, at least if the test data is similar to the training data, it's better to use the big one, which occurred only 3 times, rather than decomposing the big block into 3 smaller blocks, even if the product of the smaller blocks is unigram probability of smaller blocks is bigger than the unigram probability. The product of these 3 block probabilities is bigger than the unigram probability of this big thing, and I'm throwing away the small things using this closure restriction. So that's my current work. So the current IBM 4 decoder is pretty fast, so I'm not currently trying to improve it. So one could produce word graphs using this linear programming decoder, and then use more complex dependencies on the word graph. So then I'm not carrying out the real segmentation, which is due to memory restrictions. I'm currently thinking about how to carry out the real segmentation using the blocks. And then I have a very crude selection criteria, which is just keeping all blocks that occur twice, but still the results are very competitive. And then include some parsing into the into the clump selection on the English target side, and then using direct modeling as in Kishore Papinini's paper, include into this segmentation problem. Because segmentation problem, as I formulated it, it's independent of any, so it works in general with any cost assignment on the blocks or with any probability assignment. The problems I've been describing for the segmentation task, they exist for any for cost assignment to the blocks. Yeah.
When you're computing the language model and you're using the same block, but you're using only the English side, you cannot have problem that in two different blocks you're using the same English word, and so what you're going to decide?
So for each source clump will be generally, I will have for each source clump I will have like dozens of English target clumps, and for each target clump we will have dozens of source clumps, and this goes all into the overall search process. I'm not deciding at any point which target clump I take for translating a source clump. This goes into the overall search process involving the language model. But as it's set up, it will generally try to match as long as segment as long as possible. Yeah.
So it's the idea that you want to do the decoding in two stages. That is, when you say you're going to try out real segmentation, you want to do segmentation first and do the decoding.
Yeah, but the segment. No. So I will do the decoding, and then in the decoding I can keep track of the different segmentation hypotheses, and I will produce like a segmentation graph, and I could reevaluate the segmentation graph.
There is this notion of multi-words that is already used in some translation systems,
Right.
and speech recognition used it.
Mm-hmm.
Can you tell me how this clump business is different from having multi-words on both sides of the text?
So except like the functional form of the parameters is the same as long as you don't have gaps in the clumps. Otherwise, I'm not. So the other approaches, like the Lyman templates approach, would compute the cost for one block looking at the internal structure of the block, and like other papers using these kind of blocks do something like that. But I'm just using unigram probability of the blocks after I've selected the blocks from the training using this closure feature.
So for example, the Xinhua News Agency.
Right.
Like in the system that we had, we sort of glommed the three English words together because there was one 3-character Chinese word which always showed up against it. And so we had a clump of 1 to 3.
Right. But this,
So
yeah.
is this the same?
I mean, there are all kinds of clumps. Clump might be 1 to 3, or whatever.
Sorry, if I jump in, in the multi-words you glom the frequent ones together.
Right.
This is you look for everything.
No, I'm.
So there's a search problem. That's the difference with multi-words. That in other words, when we do the multi-words, we pre-process the data,
Yes.
and we just decide once and for all that these 3 words should be a multi-word. Whereas in your case, you're actually searching.
Right, I'm searching. I'm collecting all these possible 5 million blocks, and I'm searching about all possible segmentations. I'm not making any hard decisions at any point about the segmentation or what the target clump was.
Do you have any idea how often and in what way your blocks correspond to linguistic constituents.
For noun phrase, it looks.
Well, noun phrases
Right.
would be the usual suspect for the
Right.
most frequent, but there might be other cases, or cases where you would get a stereotype phrase that wasn't
Stereotype phrases, a good candidate as well.
It would be according to reports by.
Yeah, for example, like last week I trained on the French-English system using the Hansard date, and then you get this parliament jargon, and you get this like, dear honorable deputy or something, I would like to object to what you're saying, and then these clumps are big. I mean, you get like typical phrases that occur in these training data.
But I don't know if your training data would allow you to test that, would have parsers in.
Oh,
Does your training data have
you
parsers in
mean
the
parsing the training data and then checking how often the clumps correspond to something that is not crossing brackets in the parser?
Something.
Yeah, actually, I will be doing something like that.
Do you have the ordering information of clumps?
No,
So
I'm throwing away this.
how are you going to handle that in decoding?
But the decoder just applies these blocks. Blocks are just pairs of clumps. So I don't need this. The only thing what I need is that to which target clumps a source clump can be aligned. I don't need the internal information. So so the IBM 4 decoder would put, you could have a decoder where each source word produces one target word, but I have just a decoder that allows several source words to produce several target words. And each target clump might go with several source clumps, and each source clump might go with several target clumps. And I do have all these corresponding blocks in my in the blocks I selected during the training. But then the decision is made there are no hard decisions about this segmentation at any point in the decoder. The decision is made using this unigang probability product and the language model probability product. So I'm not segmenting anything beforehand. Actually, for Chinese English, I carried out these experiments without even segmenting the Chinese characters in the words. Right. So
You still use the alignment probabilities to decide the word ordering?
No, I'm not. I'm just taking the word-to-word alignment, and I have this closure restriction to learn the blocks, and that's it. I'm not looking inside the blocks because I think you can gain from this, but the main thing is the learning of the big segmentation units that are blocks. So you will improve the performance probably by including these word-to-word translation probabilities, but the main jump is using these blocks. And
so the final word ordering is...
You don't know I don't know. I'm not storing the internal structure. I don't know the final word ordering. I don't see it.
Decided completely by the language model.
The order of the blocks is decided by the language model. But I don't know what the word order within the clump, within the block was. I don't see this. I don't know this. I don't keep this.
Yeah, but when you output the decoding output,
Yeah.
you need some ordering. Right?
Yeah, the blocks might be reordered. So I will have, so the decoder will produce, an output like this. Blocks will be uniformly filled.
Then what about the final word ordering? Because in one clump you can have, say, 3 English words, and you don't have the order.
Right, but I'm not using the word order within the clump. I'm not interested in this because I'm just on the clump level. I'm mapping
I
these.
mean, you're not interested so far.
Right.
Because right now your results have to do with ignoring
Right.
the word order.
So the main,
Eventually, of course,
right.
you have to do it.
At
But
one-
right now, your measure of goodness does not take that into account.
No. Currently I'm producing English sentences. I don't have to reorder anything in this.
So it's
This is already the final output.
It's prescribed. When you have a block, the word
Right.
order inside it is prescribed.
Yeah, it's not.
Is that true? No, that I don't.
So the first block in the lower left corner, couldn't that be E1? Couldn't that align the first 3 words to either E1, E2, or...
Right. It might have whatever structure. So.
So you need to pick either E2, E1, or E1, E2.
But I don't need this information to generate the target.
So you pick it by the English language.
No, You mean the sets? Oh, okay. The sets are not the sets. The sets do have the ordering information, so I know. So the sets are clumps, and they go together with the. So when I run this block, I store these. I store the sequence. I don't store the sequence as a set.
So you keep
The
it
unit without the alignment.
Right. Yeah, I keep the unit without the alignment. Right.
It's a phrase.
It's a phrase-to-phrase unit. I don't look at the internal alignment.
It's a phrase-to-phrase alignment,
Right.
and the phrase stays fixed.
Yeah.
It
Right.
never permutes
Right.
or anything like that. It stays the way you found it in your training.
Right.
And so the only thing that's being reordered are the blocks themselves.
Right.
You might put don't have any money to first, or you could put it
Right.
second.
I could translate don't have any money to poor or something like that. But I cannot switch the order of the target words in this.
Right.
Did I understand correctly from your global search that the decision of how to order your eventual blocks is based entirely on the language model and not on the translation model?
In this setting, yes, because there are no source.
Well, if these blocks turn out to map to something like constituents, that's putting an awful lot of burden on your language model, since
Right.
word order can swap your
So
subject for object,
currently-
and if your language model thinks they're both perfectly plausible,
Right.
that's
So currently, for the translation direction, Chinese English, we don't do any reordering. So we just translate the blocks are in monotonic order. So we are not allowing because
Yeah, as a decoder issue.
there's an encoder issue. Right?
Okay, have you considered using word classes?
That wouldn't change anything in this. I mean, you could use classes to generalize the blocks.
So what you would do is you would not have a threshold of 2 occurrences, but
Right.
either 2 occurrences or a clump related to another clump which has occurred
Right,
twice.
more
and is
complicated. But it's
extended.
but storing all these, like, if I consider all possible blocks, then storing these block occurrences and storing the unigram probabilities of these clumps, so I cannot, it's a computational hard problem.
Okay, let's thank our speaker.
Well, thank you for coming.
You know, something the rise in the Calvin.